In this last video, I want to take a detailed look at the hydrogenic atomic orbitals, particularly focusing on their energies and shapes and how we fill up these orbitals to generate the electron configurations of heavier atoms. We'll talk about this in a few class periods, but I want to introduce it here since orbitals are fresh on our minds and we can start to see how to use these orbitals to do something that's actually useful. So just as a quick reminder, orbitals have three key properties: energy, shape, and occupancy. And the set of hydrogenic atomic orbitals in general looks something like this. So at the very bottom we have what's called the 1s orbital. The 1 is the value of n, what's called the principal quantum number. This is the n that we've seen over and over again. That's 1, 2, 3, 4, 5. It's directly related to the energy of the orbital. S has to do with the orbital shape and does have an influence on the energy. This is called the angular momentum quantum number. We see that S can be replaced with other letters. P, D, F are the most important ones as we move upward in energy. So the most important trend to notice here is, first of all, that from 1 to 2 to 3 we're moving up in energy, and secondly, from S to P to D to F, which is not shown, we're also moving up in energy. To generate the electron configuration, namely to tell us about the fate of all the electrons within an atom, we need two principles to start filling up these levels. The first is what's called the Alf Bell Principle, and it's pretty consistent with intuitive ideas. It's the idea of starting low, start at the bottom, just like filling up a glass of water, right? The water starts at the bottom and moves upward. Fill these levels with electrons by starting at the most stable, lowest energy orbitals. And the second idea is Hund's rule. And Hund's rule is a little bit tricky and not terribly intuitive. The idea here is to avoid pairing the electrons instead of pairing them up when you have a choice. So when we get up to the 2p levels where we have three different orbitals, three different psi-i's, all with the same energy, you'll see what this looks like and why it's important. So, for example, we can start at hydrogen and generate its electron configuration simply by throwing one electron into the 1s orbital. Helium is almost as simple. We put a spin down electron into that same level. It's important that these electrons have opposite spins so that the Pauli exclusion principle is satisfied. And to generate lithium, we can just keep moving up. Beryllium and boron gets us up to the 2p level. So the electron configuration of boron is what you're looking at right here. 2 electrons in the 1s level, 2 in the 2s level, 1 in the 2p level. Now, when we move to carbon, we're left with a choice. We can either put a downspin electron in the same orbital that the upspin electron is in now, or we can add an upspin electron to one of the other two levels. And it's a little bit non-intuitive to see what we should do, but Hund's rule stipulates that, you know what, we should go ahead and put that electron in one of the free orbitals before pairing up with the original electron. Intuitively, I think about this as an electrostatic repulsion issue. The electrons are both negatively charged, they repel each other. To put them in an orbital, to give them the same probability distribution so that they're likely to show up near each other in space, that introduces repulsions. So energetically, it's more favorable to leave the electrons unpaired than to pair them up. Now, as we keep moving across to nitrogen and then to oxygen, once we get to oxygen, we have no choice but to pair up an electron with that first electron we added to the 2p level. From here, we can continue to add electrons to these levels to generate new electron configurations. We'll talk about how to do this in more detail in a later class period. To end this video, I want to show you the shapes of these orbitals, the 1s, 2s, 2p, etc. And the shapes really are important because they tell us about what a molecule really looks like in terms of where its electrons are likely to be located. We'll learn later about Lewis structural models, and we'll see how we can sort of localize electrons in bonds and lone pairs. But the theory of quantum chemistry shows that things are a little bit more complicated than that. When we start putting atoms together to make molecules, the shapes of the orbitals become very, very important and in fact constrain what we can do because it's the overlap of orbitals that leads to the formation of bonds, really. So keep in mind that internalizing these orbital shapes is going to be really valuable for you. To show you what orbital shapes look like, I've pulled up the Orbitron website, and this is a really nice resource that you can use to remind yourself of the shapes of atomic orbitals. So at energy level 1, at the bottommost level, we have the 1s orbital. And here you see it just essentially looks like a circle. Imagine that the atom is sitting at the origin of these axes, and the orbital shape looks like a circle. What exactly does the circle mean is a question you should have. And the way to think about this is think of the circle as a container for high probability. So inside of the circle, there's a very high probability of finding the electron. Outside of the circle, the probability is relatively low. There's some cutoff value associated with this, and this can vary in different pictures of orbitals that you see, but generally it's something like 90 or 95%, which tells you that 95% of the time you will indeed find an electron that is in or is characterized by the 1s orbital inside that sphere. The 2s orbital is spherical just like the 1s orbital. In fact, that's where the s designator comes from. But notice that we have a slight sliver in here of density of the opposite sign, and that's what the color means here. We might say that the wave function is positive in the blue region and negative in the red region. Now, because probability is the square of the wave function, the sign of the wave function doesn't have too much to do with probability. But when you start combining orbitals, the sign of the wave function does become very important. So here we have a sphere just like the 1s orbital, but a kind of donut-shaped hole in the middle of the opposite sign. The 2p set of orbitals introduces a totally new set of wave functions. So remember, there are 3 degenerate orbitals for the 2p level. There's the 2pz, 2px, and 2py. And you're seeing these 3 right here. They're sort of dumbbell shaped is the way I like to think of them. And notice that we have 2 regions with opposite sign of the wave function. Just like for the 1s and 2s orbitals, inside of these shapes, we have a high probability of finding the electron, and outside of these shapes, we have a low probability of finding the electron. And notice that the z, x, and y orbitals differ in the orientation of the dumbbell. So the sort of axis of symmetry is what defines the label. So we have 2pz on the left, 2px in the middle, and 2py on the right. The 3s and 3p levels essentially follow the patterns we've seen already. Notice there's another sort of new sliver at the center of the 3s level. The 3p level looks fairly similar to the dumbbell-shaped 2p level with an additional node or additional area where the sign changes, kind of sneaking in there within each dumbbell. And then the 3d orbitals gets us to the first set that is unique in having the d angular momentum designator. And these look a little bit odd. For the 3d orbitals, we again have these lobes that are regions where there's a high probability of finding the electron and outside of which that probability is low. And as before, where you see different colors, think of different signs of the wave function. Is it positive or negative? Red and blue or vice versa tells you whether that's the case. Briefly, I'll mention the 4f orbitals, which are important for the lanthanide and actinide series. And these look, again, very complicated, sort of like the d orbitals on steroids. But once again, interpret these in the same way that you would interpret an s or a p or a d orbital. Inside the container, inside the surface, we're likely to find electrons. And the color of the surface tells you the sign of the wave function within